So basically, in this talk, I want to sort of give an overview of some work of some people that kind of include myself about quantization of character varieties on their relation with topological field series. And so I hope the first half of the talk will be somehow colloquial and easy to understand. And then I want to talk a little bit about some work in progress that I'm doing right now about something I want to call a quantization of the Riemann-Hilbert correspondence, but it's probably pretentious. So I'll tell you a bit about that. So basically, I want to start by recalling some well-known point of view on the representation category of quantum groups. And then I want to talk about quantization of character varieties and somehow explain that in a way you can extend all of this point of view on the representation theory of quantum group to sort of arbitrary surfaces like this. All this thing are in fact about the disk, and you can extend this to arbitrary surfaces and you get similar pictures. And then I want to talk a little bit about this quantum Riemann-Hilbert correspondence, which more precisely it's a generalization of the Kohno-Drinfeld theorem that we heard a little bit about yesterday. So let me fix a simple or maybe a reductive complex algebraic group on some complex number, which I will assume is generic. So if you want to think about G as being SL2 or GL2, that's perfectly fine. Everything sort of generalized nicely for the group. And what I call RUBQG is a category of so-called integrable modules over the corresponding quantum group associated with G. So associated to G, you have a Hopf algebra called UQG, and I take the category of finite dimensional, or more precisely locally finite dimensional, like direct sum of finite dimensional modules. And the thing that you should think about it as a Q deformation or some sort of quantization of the representation category of G. And one way to think about that is that actually the underlying category is the same. So RUBQG is equal or isomorphic to RUBG as a category, but it has a very non-trivial and interesting monoidal, or in fact braided monoidal, or in fact ribbon structure. So one reason we like this sort of categorical structure, as everybody knows, is that you get representation of braid group on some invariant of links, on more general invariants of tangles, and those are like vast generalization of the Jones polynomial. So in particular, all of that as a nice relationship with Chern-Simon theory that will be sort of in the background of this talk somehow. So somehow this was like the original definition of RUBQG. This was says a representation theoretic definition. So you have a Hopf algebra and you take modules over this Hopf algebra. And but somehow the nice thing that this category with its square monoidal structure is actually less information than quantum groups. And in a way, that's a good thing. In a way, it's more canonical. And it's a good thing because there are many other constructions of that same category that somehow do not involve representation theory. And they can be useful for various reasons. So you have different point of view on this category, and somehow only one involves like taking modules over Hopf algebra. So somehow you shouldn't think about quantum groups themselves, but I really want to think only about the category. And it turns out that many constructions that seem to involve quantum groups, in fact, depends only on the category. And I claim that this is a good thing somehow. This is more invariant. So in particular, there is a construction of that category from something called skein theory. So again, this is something that works for arbitrary group, or in fact, arbitrary ribbon category. But let me focus on SL2 just for this example, because it's somehow much simpler and very, very explicit. And the basic idea is that maps between this category. And so this every tangles gives you a morphism in this category. That's how you get representation of braid group on that invariant. And somehow the claim is that in fact all morphisms are of this kind. So you have some sort of quantum version of Chauvel duality that tells you that every morphism between tensor power of this defining representation or the quantum analog of the defining representation are actually the image of some tangle. Well, you know, the classical Chauvel duality tells you that this is basically the symmetric group or something like that. And this is a quantum version of that. So in particular, you can, in particular, this thing satisfies some relation. So it turns out that V is self-dual as a representation of UQSL2. And the thing that every complicated tangle can be simplified using something called the Kaufman-Skine relation. And so at the end of the day, you just get like a bunch of identity maps and then composition on cup and caps with some coefficients. So you can sort of unbraid everything. And you can write on everything as a linear combination of those guys. So basically, one thing you can do is you can sort of formally define a category called the temporal category, whose objects are finite sequences of points. I said on a disk because I want to do the same thing on the surface after that, but you can just think of it as a sequence of points. And morphisms are just framed unoriented tangles, and you just mod out by this relation. And this Chauvet duality translates to the fact that if you do that, you essentially recover up QSL2. So some sort of folklore theorem, and there's this very nice paper by Tingley called a minus sign that used to annoy me, but now I know why it's there, which does exactly what it seems to do. So it got all the signs right. And the theorem is that if you take this category, which is defined in a purely diagrammatic way, and we sort of formally complete it by adding splitting of idempotent, which is something called the Caribe completion, and just formally add arbitrary direct sums, then you get something which is equivalent to RUBQ-SL2. So this gives you a construction of this category in purely topological way, which doesn't involve representation theory at all, which is nice. So somehow the claim here is that the knot invariant you get from RUBQ-SL2 actually are enough informations to recover this category completely. So again, it doesn't recover the quantum groups themselves, but only the category of representation. And then there is another point of view, which is by far my favorite, which comes from conformal field theory. It's also known as a Drinfeld-Kontsevich integral. So you define a category, which I want to denote rep phi of G. So as a category, this is just rep G, and you sort of extend trivially the morphism by taking formal power series in H bar. And you just keep the same tensor product. So it seems you're doing nothing. But then you can put a highly non-trivial braided structure, which comes from something called a Drinfeld associator, which is a formal power series into non-commuting variables satisfying a complicated set of equations, which is related to Maclaurin pentagon equation of monoidal categories. So you sort of plug this thing, which is very complicated object, and you get a braid monoidal category. So it's not obvious at all that such thing actually exists. And in fact, the only way we know of how to prove that associators actually exist, they come from some like geometric or analytic construction. And the first and for a long time, the only sort of explicit construction of an associator we had comes from the monodromy of the so-called Knieznik-Samolotchikov equation in conformal field theory. So that's how Drinfeld showed that the set of associator is non-empty. And I should say that there is another remarkable construction of an associator, which is also analytic and comes from Kontsevich formality, and is due to Alexeyev and Torosian. So in both cases, the thing you get, so you get those formal power series, and the coefficients are like very, very complicated thing involving horrible integrals and whatnot. So everything is transcendental and highly non-explicit, but somehow you can use this as a black box. So you pick an associator, it exists. You don't want to know what it looks like, but you pick one. And then somehow the fact that it works, the fact that you get some braid monoidal structure is kind of obvious. It really comes from you are integrating a connection on the configuration space of points. So you get representation of braid groups. And so the fact that it gives you a braid monoidal category is kind of sort of obvious. And so the nice thing about that is that in a way it's like much more clear than the construction involving quantum group. And in particular, it works for arbitrary algebras as long as you have an invariant symmetric pairing. And there's also some sort of universal version where you don't pick a specific Lie algebra, but you take some kind of Feynman diagrams that are universal for the algebra with a symmetric pairing. And I can sort of do that at this universal level. And if you do that, you recover the Kontsevich integral of knots, you prove something called the formality of the little disk opera, and it has a lot of very, very nice application. So in ways, I claim that this construction is very conceptual. It doesn't involve like writing down explicit formula like what happened for quantum groups. And the very nice thing that you actually get the same thing. So there's this theorem by Kohno-Drinfeld, which says that actually, if you start with a reductive group and you apply this construction, the Braid monoidal category is equivalent to RUBQG. So this is interesting in both directions. Sort of the original motivation is that it gives you an explicit computation of the monodromy of this important KZ equation using quantum groups on quantum matrices. So that's your, yes?
Just a small question.
Sure.
For this category, you probably still want H to be kind of small, right? Or even I'm not sure if you take arbitrarily large representations, then I'm just wondering, kind of does it really work non-formally for some concrete Q?
Yes, I mean, if you just pick some associator, then this is here H bar is supposed to be a formal variable.
Yeah. So when you write a formula Q equal to exponential of H bar, what does it?
Yeah, sorry, that's kind of sketchy. Here I want H bar to be a formal variable. Mm-hmm. Okay. And then Q exponential, in that case, Q is a formal power series.
Okay.
And then I claim that if you don't pick a random associator, but like the one coming from the KZ equation, then actually it works for when H bar is an actual complex number.
But it varies. But some does it?
Yeah, if you take finite dimensional or locally finite dimensional representations.
But then for all of them, would it work for all of them?
No, it wouldn't work for all of them.
Okay.
Formally, it works for all of them. On the specialized version, works only for finite dimensional, basically.
Okay. Thank you.
Anyway, so I was saying, so somehow a more important reason why I like this theorem is that gives you an explanation of why this representation category of quantum group exists. And again, it really somehow only describes this category, not quantum groups themselves. We learned yesterday from this very nice talk by Xiao Meng that if you actually want quantum groups on R matrices, you need to consider much more complicated differential equation involving like non-regular singularities and stuff like that. So somehow this construction is kind of complicated, but it's as simple as it can get somehow. And if you just care about the representation category of quantum group, you don't need anything more than that. And then there is some sort of, I should say, a precise version of why you should think about this category as a quantization. So again, it's not that quantum groups themselves, they quantize some Poisson structure, but I want to think of this category RUBQG as a quantization. And so you can take something which looks like a quasi-classical limit in the ordinary sense, where you formally put Q equal x1 plus h bar, and again here h bar is a formal variable. But if you just put Q equal 1, you get RUBG, where the braiding is actually symmetric. And here somehow you measure the first order non-symmetric term, basically. So this difference is equal to h bar t plus higher order term in h bar. And as was explained in Claudia's talk here, t is the canonical element with respect to the killing form. So for a while, you get something that people, used to call for a while an infinitesimal braid monoidal category. So you have RUBG, the classical RUBG, and this element T, and people were like, okay, you should think about this as some sort of Poisson, some sort of categorified Poisson algebra. That this is a symmetric monoidal category, and the braiding is a deformation of this T. So this should have some sort of Poisson algebra, and RUBQG should be a quantization of that. And one way to make that precise is using this shifted Poisson structure that Claudia mentioned earlier. So first of all, there is a geometric interpretation of this category. You should think of representation of G as being quasi-coherent sheaves on the classifying stack of G. So if like me, you're not familiar with stack, I'm just saying that Well, a quasi-coherent sheaf on a point is just a vector space. And then if you take the quotient by G, it just means that you want to work G equivalently, so you want to have an action of G on that vector space. So basically, representation of G are just sheaves on that, basically. And again, as Claudia told us, BG has a so-called two-shifted symplectic structure. And in a very precise sense, RUP-QG is a quantization of that. Maybe somewhat better, RUP-phi-G is a quantization of this symplectic stack, which comes from something called the formality of the little disk opera. So there is something a bit surprising that this shifted Poisson structure are actually somehow easier to quantize than ordinary one. And in particular, every associator gives you a canonical way to quantize two shifted symplectic structure, and this is what you get when you apply this construction. Okay, so now let's, the main character of our talk, pun intended, so let S be a topological surface. So what I call the representation variety is the variety of all representation of the fundamental group of the surface into G. So S should be oriented here, I didn't say that. And the so-called character variety of S is just the quotient of that by the adjoint action of G. So again, there is an important feature of this character variety is that the carrier is a canonical Poisson structure, which is very much related to Chern-Simons theory as well, where basically the Poisson structure comes from sort of integrating the Killing form. And what I mean by canonical is that they are really topological invariants. So the Poisson structure is invariant by diffeomorphism, and it really depends on the surface, not just of its fundamental group, while the character variety as a geometric object depends only on the fundamental group, but the Poisson structure somehow is sensitive to the actual surface. And it turns out that there are several approaches to the quantization of this Poisson structure, and they all have like nice feature on like less nice features in a way. So there is a combinatorial approach by Alexeyev, Gross, and Schomerus, where they give very explicit description of something that they call the moduli algebras. So this gives sort of explicit quantization of these character varieties. But the thing that the sort of topological features that you would expect from such quantization are kind of hard to see in that framework. And also originally they were not defined for closed surface. So there was some guess as to how it's supposed to work, but it's not completely easy to write it down. And then there is an approach using skein theory on something called skein algebra. And they are nice because they are topological by definition, but they are very hard to handle algebraically. Like already for SL2, in many examples, we don't know how to compute skein algebras at all. And then there is an approach using associator, which is due to Liebland and Shevera, which is in a way much more general. The contains like various variation of character varieties with various decoration. And in a way, they are like they are similar to this Alexeyev Gross Schomerus construction, but they are on the other side of the Kohno-Drinfeld theorem. Anyway. So a sort of important observation is that while the character variety of a point is of course trivial, I want to think about this as, again, a simple example of stack. And since the representation variety of a disk is a point, this quotient is the quotient of point by G, so it's nothing but BG. So the sort of moral is if you, instead of taking like global function on the character variety, you think about sheaves on character varieties, then this category of sheaves, they are obtained by gluing together copies of RUP-G in some sense that I will make a little bit more precise later. So again, I should emphasize that this is very non-true for the algebra of global function. Like function on character varieties that do not glue well, but category of sheaves do, which is one of the reasons we want to consider that. And in fact, you can package this very nicely on this theorem due to Ben-Zvi, Francis, and Nadler, which says that the functor that take a surface and attached to it a category of sheaves on its character variety is actually part of a two-dimensional topological field theory. So more precisely, it's like a twice categorified TFT. So it's something that attaches categories to surfaces, not vector spaces or number. So really, you should think of this as being the two-dimensional part of a would-be four-dimensional TFT. But it turns out that it does not extend up to dimension 4. So you don't get number for four-dimensional manifold, but you get vector spaces for three manifold, and they are basically the classical version of skein modules. And to sort of quickly connect this with what happened in Claudia's talk, but you probably already noticed that this is some sort of linearization of this Poisson sigma model with target PG. So linearization because instead of attaching to S some geometric object, like the character variety itself, you take its category of sheaves. And so again, this is very much related to Claudia's talk. One nice thing that the Poisson structure is actually behaves well under gluing. So the first observation is that the character variety of S1, or equivalently S1 cross I, is just a question of G by itself. Okay, the fundamental group of S1 is just Z, so you just need to know where you send the generator. So the representation variety is G, so the character variety is G mod G. And if you have an arbitrary surface with a circle boundary, you have a map that sends, a representation of your fundamental group to the monodromy around that particular boundary component. And so this gives you a map from the character variety of S to the character variety of S1. And this is something that is called a multiplicative moment map. So it's a multiplicative version of the classical notion of moment map in Poisson geometry. And this also has a nice interpretation in Claudia's language in shifted Poisson geometry. The claim is that the character variety of S1 is actually one shifted symplectic, and this map has a Lagrangian structure. And I want to emphasize that in this sort of stacky world, being Lagrangian is not a property; it's actually extra structure, and this structure like pack nicely in one single object, both the Poisson structure and the character variety and the multiplicative moment map. And then there is this abstract formalism that tells you that gluing surfaces together is the same as like taking Lagrangian intersection, as Claudia explained. And it turns out that in this particular example, and this is due to Kalak and Safronov, this recovers something which is sort of easier to handle and more classical. And if you glue your surface along two intervals, this corresponds to a general construction called fusion, which was introduced in the framework of so-called quasi-Poisson geometry by Alexeyev, Kosman, Schwarzbach, Malkin, and Meinerken. And similarly, gluing a disk to seal a hole corresponds to a multiplicative version of Hamiltonian reduction. So there is a sort of much more general version of that, which tells you that if you have any reasonable Riemann category, then there is an assignment to any surface of some category, which I denote by this symbol, integral over S of A, which can be computed using factorization homology. So this thing has very nice property. So in particular, the image of the disk is nothing but A itself, and it's functorial with respect to embeddings. So in particular, if you pick an embedding of the disk into your surface, you get a functor from A to the category attached to that surface, and this carry action of the braid group of S. And one way to think about this construction is that basically this category is sort of the universal extension. So A carries representation of the usual braid group. And this integral of the S of A is like the universal extension of this representation to representation of the braid group of your surface, basically. So in a way, they are characterized by some universal property with respect to the braid group. And in particular, some sort of like more down-to-earth way to think about that is that it's some sort of function version of what Walker called a skein category. So it has object just collection of points on S, and morphisms are just framed oriented tangle on S, or maybe knotted graphs. Sorry, decorated by morphism of A and modulo some local relation. So in particular, you have a really sort of easy diagrammatic way to think about that. And if the category is semi-simple, which is the case of RUB-QG, then those are pretty much the same, basically. And the claim is that if the category you choose is RUBQG, then this provides a canonical quantization of character varieties. Again, by canonical, I mean that this is a purely topological construction. Like you don't make any choice. You just get something which is functorial, basically. So it turns out that this construction satisfies the action of a two-dimensional TFT in a very, very strong sense. Like it satisfies more than the usual action of TFTs. And this sort of translates as follows. If you choose an interval on the boundary of S, then this category becomes a module over A. So A is a braided monoidal, so in particular monoidal category. So it's some sort of categorification of an algebra. Okay, it has something that looks like a multiplication, which is associative up to isomorphism. So we have a fairly straightforward notion of module over that, which is just a category that carry an action on A of A, and this is associative up to isomorphism. And so every time you pick an interval on the boundary of S, you get such a module structure on this category. Another claim is that if you glue two intervals together, then this corresponds to take what I want to call the trace with respect to A. So if you pick two intervals, you get two A module structure on your category. And it's not hard to see that actually you get some categorified version of a bimodule. And this trace is a categorical version of the trace of a bimodule, sometimes called the cocenter, where you somehow mod out by A m minus m a for any A in A on any m. So basically, this is a thing where you take a bimodule and you take the quotients, the sort of largest quotient in which the left and the right action of A agree. So you forced somehow the left and the right action of A to agree. And maybe this form is slightly more familiar to you, but if M and N are respectively a right and a left module, then this sort of linear or absolute tensor product becomes a bimodule, and in that case, the trace is just the tensor product over A. So in particular, if your surface has two connected components, and you choose an interval on each connected component, then each connected component is associated a category, and gluing along this interval is really just taking the tensor product over A. So this sort of formula is maybe more familiar, but this one is kind of more general because it allows for like self-gluing as well, like when the two intervals are on the same connected component. And every time you have a circle boundary, you get something called a braided module category over A, which is a sort of concrete version of what people call E2 module, like module over an algebra over the little scoparad. And then there is some sort of categorical version of like trivializing the monodromy around the second boundary. So you get a module structure, and a loop around the boundary gives you this braided structure on this module, and then there is a sort of categorical version of trivializing the monodromy, which corresponds to like sealing a hole. So, okay, I apologize for the very bad picture. It was kind of a last minute thing, but so basically at the top, I have like two intervals on some surface. On the blue points are objects of the category attached to the surface. On the red points are elements of A. And somehow the action is given by like mapping these points near the boundary here. So here you have a right action, here you have a left action by just adding points near the boundary. And when you glue those two intervals together, well, this says like basically there is no difference anymore between like acting on those blue points on the left or on those blue points on the right. You can take your red point and like move it around, like from one side to the other. So this really says that gluing those intervals together is really just somehow identifying the left and the right action. So anyway, the details don't matter too much. The sort of thing you should remember is that there is a sort of explicit algebraic rule that allows to compute what happened when you glue surface together. And so in particular, every punctured surface can be obtained by gluing simply connecting things, so disks along interval. So if you choose such a decomposition, so this is not canonical, of course, but you can choose one. And one of our theorem with David Ben-Zvi and David Jordan is that every time you choose such a combinatorial decomposition of your surface, then you get an equivalence between this category and some very explicit category of module for some algebra. So more precisely, internal module in A. And again, AS is not just some abstract algebra. This combinatorial decomposition gives you like a very explicit presentation somehow by generators and relation. So in the particular case where A is rub QG, for the annulus, you get something that people call the braided dual, which is important in representation theory. And for the punctured torus, you get something called the algebra of differential operators, which is also known as the Heisenberg double of the quantum group. And so this is an algebra which was introduced by Semenov-Tianshansky, which is also important in representation theory. And in general, this actually recovers this combinatorial construction due to Alexeyev's that I was talking about before. So this moduli algebras. So again, the important fact that this category is completely canonical, and then the algebra is not. On some of the important points that we get this algebra as the output of a topological construction. We start with a category which is canonical, and we get this algebra as a sort of particular computation of those categories. Now we also have a version for closed surface, and so the sort of claim is that this notion of braided module category that I was mentioning really quantize this notion of multiplicative moment map. So we show in general that if you have an algebra in A and you take this category of modules, then braided module structure on that are the same as moment map, quantum moment map from this braided dual to A. And in particular, if you want to compute what you get for a closed surface, then you just remove a disk in it, use our computation to realize that as module over some algebra, and then the monodromy around the puncture gives you a moment map from OQG to that algebra. And then you just take the full subcategory of all module on which OQG acts trivially through this moment map. So this is a bit cumbersome, but this is very, very explicit. You can really compute what you get this way. So in a way, I claim that these categories are quantization of this character stack. So they are deformation of category of sheaves on the character variety. And then there is some analog of the global section functor. And if you apply that, you get an actual quantization of the variety, like a quantization in the usual sense. Like the algebra of global function on the character variety is a Poisson algebra. And if you apply this global section thing, you get a quantization of this Poisson algebra in the usual sense. And if you combine this with Cook's result I was mentioning before, in particular, this shows that this algebra is actually isomorphic to the scaling algebra of S, which I think is something sort of people suspected, but I don't think this was proven before that. I might be wrong, but I don't think it was. And again, some of the sort of slogan that you should remember is that scaling algebras are not compatible with Gling, but scaling categories are, which is why it's better to work with them. Okay. So during the last minutes, I want to say a little bit about this quantization of the Riemann-Hilbert correspondence. So if you start now with a Riemann surface, so with a, let's say, a closed topological surface together with a complex structure.
Hello?
Say again? Okay, I thought I heard something. So yeah, so let S be a Riemann surface on pick a finite set of points on S. Then the Riemann-Hilbert correspondence is a formal isomorphism between the character variety of S, where you remove the small disk around each point, and the moduli stack of meromorphic connection on S, which are holomorphic away from the point of P, and which are sufficiently irregular at point in P. So again, this is like the easy version of the sort of thing that Jaume was talking about yesterday. So I only have like regular singularity. And then if you have such a connection, you can take its monodromy, and it gives you a representation of the fundamental group. And this is exactly the map that goes from the left-hand side to the right-hand side. And it turns out that it's an analytic isomorphism, but it's not algebraic. So if you want this to be something algebraic, you need to take like formal completion. So you need to take the formal neighborhood of the trivial connection here, and the formal neighborhood of the trivial representation here. So that's what I'm implicitly doing. And of course, the character variety carries an action of the bread group just by moving the boundary component around, or even an action of the mapping class group. And it turns out that there is also an action on the modular stack of flat connection. So basically, what you can do is you can pick a connection which are regular singularities at some point, and you can start moving the points, but forcing the connection to the monodromy, to say the same. And this is something called isomonodromy. So in particular, you get an action by moving the point around, and this gives you an action of the break group. And one sort of remarkable fact is that the Riemann-Hilbert map is actually equivalent with respect to the action of the break group. So this is kind of funny, but it sort of comes from the fact that the right-hand side is completely topological, so it gets an action of the mapping class group by definition. But the left-hand side a priori depends on the complex structure. But because it's isomorphic to something that doesn't, it means that if you start changing the complex structure, actually you're doing nothing. Like changing the complex structure should give you an isomorphism between those two things, basically. And there is another remarkable result that says that this Riemann-Hilbert map is actually a Poisson map if you formally identify the moduli stack of flat connection with the right-hand side here. Okay. So the Atiyah Bott structure on the character variety is actually pretty complicated, and I claim that you can formally identify the moduli stack of flat connection with some much simpler Poisson manifold, which is given by a direct product of cotangent bundle with its canonical symplectic structure on dual of G with the so-called Kirov-Kostanov-Shoyo linear structure, and you mod out by G. And so basically the T star G to the power of G, where G is a genus of the surface, is like correspond to a basis of the homology of your surface, and those correspond to the residue at the singularities. And the claim is that this thing is actually isomorphic as a Poisson manifold to the character variety. And the map is given by the Riemann-Hilbert correspondence. So there is actually a combinatorial version of that, which is also due to Alexeyev, Malkin, and Meinröcken. And the sort of high-level explanation of that is that there is a formal isomorphism of one shifted symplectic stack from little g star mod G to capital G mod G. And the sort of thing that you can do with that is that you can take a Poisson manifold with an ordinary moment map, which in this picture is sort of as a Lagrangian in this G star mod G shifted symplectic stack. And you can just compose with this isomorphism to get a multiplicative moment map. I recover something that Alexeyev and Kosmal, Schwarzbauer, Malkin, and Meinröcken call exponentiation of quasi-Poisson manifold. And so again, being Lagrangian is some structure, and as I said, part of this Lagrangian structure is actually the Poisson structure on the source here. So it's not completely obvious, but it just happened that the two Poisson structure on X mod G that you get this way are isomorphic. Okay, so you just take an ordinary moment map and you turn it into a multiplicative moment map, but somehow you then change the Poisson structure. And this is compatible with two different notions of Hamiltonian reduction on both sides. And those people, like say Meinröcken and Woodward and Naef, they show that it's also compatible with this operation I called fusion before. So this sort of generalized, this particular case of Lagrangian intersection. And it turns out that using this, basically, you can prove a combinatorial version of the Riemann-Hilbert Poisson isomorphism, which I think should be thought of as some sort of limit of the Riemann-Hilbert correspondence, but I don't have a precise statement about that. Anyway, so you get a combinatorial version of this isomorphism from Poisson isomorphism from the character variety with its Atiyah Bott-Poisson structure to something much, much simpler. So the claim is that if I start with an algebra and I have an algebra map from U of G, which, so as you know, U of G is, you can think of it as a quantization of the linear Poisson structure of G star. So this typically arises as a quantization of a moment map. And the sort of claim is that, so remember that this category rub phi of G is constructed by just taking the same category with the same tensor product and then plugging an associator to get a non-trivial braided monoidal structure. I claim that you can play the same game with this category. You take just the same category with the same action from rub G, and you can plug an associator and get a non-trivial braided module category. And somehow what I claim is that this construction quantizes this exponentiation I was talking about on the previous slide. And the fact that you really start with the same category, but only change the braided module structure, it quantizes the fact that when you turn an ordinary moment map into a multiplicative moment map, you don't change the Poisson structure. So the fact that the category is the same, it quantizes the fact that the Poisson structure is the same. And I won't go into detail, but basically this is compatible with quantum fusion. So it means that if you apply this construction to elementary pieces and like starting gluing these things together, you can actually compute the result by computing the trace of a bimodule that does not depend on the associator. So something which is much, much simpler. So this is a bit abstract, so let me just give some an example. So if you take the case of the punctual torus, in particular, you get, first of all, you get an isomorphism between factorization homology over the punctual torus of rho phi G with DQG mod. So the first isomorphism is just the original Kohno-Drinfeld theorem. So you can apply our result to this category in the middle as well, and you get some complicated algebra in this complicated category, and you get an equivalence like that. So somehow the new part is like the second isomorphism, where you have this category which a priori depends very much on the associator, and I claim that as a category, it's equivalent to something that do not involve associator at all, and just involve this algebra of differential operator on little g, which is just the veil algebra. And this category do not depend on the associator, but the action of the braid group of the punctual torus does. So it seems that I've treated something complicated to for something equally complicated, but in fact I claim that the formula for the action of the braid group are much, much, much easier to compute on the right-hand side here. And again, the right-hand side here, you should think of it as a quantization of T star G mod G. Of course, D of little g is a quantization of the contingent bundle of G. And if you take equivalent module, this is a quantization of this quotient stack. So the thing in the middle is, again, a quantization of the character variety, and this thing is of the punctual torus, and this is a quantization of T star G. So this quantizes this Riemann-Hilbert Poisson isomorphism. So on the, okay, this will be my last slide. It goes up to 21 just because I have some blank slide at the end in case there is questions, but this is the last one. So in particular, I get this way explicit formulas that involve associator for representation of the braid group of the punctual on the closed torus. This was actually my main motivation for this. The sort of remarkable thing is that you can, this formula are fairly easy to compute, and you can do this purely diagrammatically. And you recover a formula by Kalak, Enriquez, Ettinger for something they call elliptic associator, which gives an explicit formula in terms of ordinary associator for the monodromy of the KZB equation on elliptic curves. So in particular, you can also do that for higher genus surfaces. So I claim that you get explicit formula for higher genus associators, although it's still a work in progress. So the first part is definitely done. The formulas for this higher genus associator are work in progress. But using the equivalence of the previous slide, you also get a description of this braid group representation in terms of DQG. So in particular, it gives you a higher genus version of the Kohno-Drinfeld theorem. So it turns out that for the torus, we know by this work by Kalak, Enriquez, Ettinger that it computes the monodromy of the KZB equation. In higher genus, this is not known, but of course, I suspect this is true. And it's kind of well known that the KZB equation on Riemann surfaces is a quantization of this isomonodromy action I was talking about before. So that way, this construction should be stood as a quantization of the moduli stack of flat connection together with a quantization of this isomonodromy action. And there is also a very recent, very cool paper by Campos, Idrissi, and Vilvara, where they compute some some sort of not formality, but some analog of the formality of the little disk operad for configuration spaces of surfaces, where they show that they are equivalent as modulo operads to some very explicit complex of graphs. And I suspect, or rather Najib Idrisi told me that this should be, my result should be related to there by some sort of causal duality. So this is another interesting application. And I'll stop here. I'm sorry again for the technical